L'Hopital's rule works when you have 0 over 0 or infinity over infinity. In this case, as x tends to infinity, 2 to the x will grow without bound, so will 3 to the x, and so we have infinity over infinity in this limit. So we can apply L'Hopital's rule, which says that we'll have the limit as x to infinity of, let's see, the derivative of 2 to the x would be 2 to the x ln 2, and the derivative of negative 5 is 0. The derivative of 3 to the x is 3 to the x ln 3, and the derivative of 3 is 0. So now, as x tends to infinity here, let's combine these. We have basically 2/3 to the x, because we have 2 to the x over 3 to the x, and now ln 2 over ln 3. But we have a base here that's actually less than 1. So since our base is less than 1, if you take a number that's less than 1 to higher and higher powers, you're going to get 0. So the limit in this case is 0. Basically, the bottom is outgrowing the top and pulling us to 0. So L'Hopital's works in the case of 0 over 0 and infinity over infinity. It doesn't always work, which is kind of a drawback to L'Hopital. So it can be easy and simple, but it may not necessarily give you a result. In this case, notice that we have e to the x minus e to the minus x over e to the x plus e to the minus x. Now just to kind of remember, let's draw the graph of e to the x. E to the x looks like this, and e to the minus x is that graph flipped around the y-axis. So the minus x would just be doing the reverse. So as x tends to infinity, then this term fades, and we have e to the x growing without bounds. So the top is going to infinity. The bottom is also going to infinity because this term grows quickly and this term fades away. So we have infinity over infinity. And so we can use L'Hopital's rule since we have that indeterminate form. So we get the limit as x tends to infinity. We take the derivative of e to the x, we get e to the x. The derivative of e to the negative x kicks out an extra negative, which makes this plus e to the minus x by the chain rule. The derivative of e to the x is e to the x, and the derivative of e to the minus x is minus e to the minus x. Except for, again, we have infinity over infinity. So let's apply L'Hopital's rule here, and we'll have the limit as x tends to infinity. Let me take the derivative of the top. We get e to the x minus e to the minus x, and e to the x plus e to the minus x. So we're back to where we started, so L'Hopital's isn't helping here. We're just cycling around. And sometimes you can cycle around, or you could actually maybe kind of spiral out of control. Just the derivatives just keep getting more and more complicated. They look worse and worse and worse. So, so L'Hopital's may not work. In this particular case, what we could do is we could say to ourselves, well, since e to the x is the fastest growing term, I can stop the denominator by dividing top and bottom by e to the x. So I could start here, and without using L'Hopital's, divide top and bottom by e to the x. That gives me the limit as x tends to infinity of e to the x divided by e to the x would be 1 minus e to the minus 2x, and 1 plus e to the minus 2x. Both of these fade away, and we get 1 over 1. So the limit's actually 1, but we couldn't find it with L'Hopital's. Here's an example. If we look at this, we have x squared, so as x goes to infinity, that's going to grow without bound. But we also have this e to the minus x, which is going to get small. So we have infinity times 0. Now you might look at that without thinking clearly and say, well, since this number is bigger, is infinity, should infinity times anything be infinity? Or you might say, infinity times 0, that should be 0, because 0 times any number is 0. But it's not necessarily so. This is another indeterminate form, because what we're really saying when we say the limit is infinity times 0 is that these numbers, the x squareds, are getting bigger and bigger without bound, and these numbers, the e to the negative x's, are getting smaller and smaller. They're getting closer and closer to 0. So we don't necessarily have infinity times 0. We have big numbers times small numbers. And what you get when you multiply a big number times a small number depends on how big is the big number and how small is the small number. So when you just get infinity times 0, this is indeterminate. You can't tell what's going to happen when you as x tends to infinity. But it's not the kind of indeterminate that form that L'Hopital's applies to, right? You can only use L'Hopital's if you have 0 over 0 or infinity over infinity. So L'Hopital's only works for these two. But don't give up. What you can usually do is kind of rearrange a little bit until L'Hopital's does work. See, if you have, say, an infinity upstairs, you could divide by the reciprocal, and that would give you a 0 downstairs. Or if you have a 0 upstairs, you could divide by a reciprocal, and that would give you infinity downstairs. So we have little tricks for rearranging. In this case, we could write this as the limit as x tends to infinity of x squared over e to the x. Right? E to the negative x could go down here and be e to the positive x. Now both of these are growing, and so we have the indeterminate form infinity over infinity, and L'Hopital's applies in that case. So once we have infinity over infinity, then we can apply L'Hopital's. So L'Hopital's says this would be the limit as x tends to infinity of 2x over e to the x, taking the derivative top and bottom. Again, that's infinity over infinity. So let's go ahead and apply L'Hopital's and say that's the limit as x tends to infinity of 2 over e to the x. Finally, the top is constant and the bottom is growing, so we have 2 divided by larger and larger numbers. That limit is going to be 0. We could have tried it the other way too. So our approach was to take this 0 and put its reciprocal downstairs. So 1 over 0 then made infinity. We could try it this way too. We could say, all right, well, this is e to the negative x upstairs and 1 over x squared downstairs. So now we have an indeterminate form, whereas x tends to infinity, the top tends to 0, and the bottom tends to 0. So L'Hopital's applies in this case. So, however, if we do apply L'Hopital's, things don't get better, they get worse. So we kind of rearrange the wrong way. So the derivative of the top is e to the negative x, but the derivative of the bottom is negative 1 over x cubed. Uh-oh. So, whereas before, when we rearranged this way, the powers could slowly decrease until we could take the limit by just inspection. But here, these powers are increasing. If I'm still getting 0 over 0, but every time I take a derivative, this term in the denominator is actually getting worse. So this way doesn't work. So we'd have to go back and try rearranging a different way if we were wanting to use L'Hopital's. So we see the way to do it in that case. Now the fact that the limit as x tends to infinity of x squared over e to the x turned out to be 0 here means that e to the x must have been growing faster than x squared. Sort of like they were both racing to infinity, but e to the x was able to grow so fast that even though x squared was growing, it still pulled the quotient down to 0. So this just shows that e to the x grows faster than x squared. In fact, we could consider how does e to the x grow compared to any other power of x. Now, of course, if k is 0, then this would just be x to the 0, which is 1, and there's no contest at all. This would get pulled to 0. But if k was less than 0, then rightfully this would be the limit as x tends to infinity of 1 over x to some positive power, right, which would be the opposite of k since k is negative. So now they're both going to 0, so that's obviously 0. What about if we have x to some positive power then? Let's consider that case. Well, we have here a form that will be infinity over infinity, and so L'Hopital's rule will apply. And so when we apply L'Hopital's, we get the limit as x tends to infinity of k, x to the k minus 1, and the derivative of e to the x is just a plain e to the x. Okay, now, if k minus 1 is now negative, right? Notice the power has decreased, so if k minus 1 is now negative, then really this goes downstairs and we're talking about one of these limits that will clearly be 0. But if not, then we still have infinity over infinity, and we could apply L'Hopital's rule again, and the power on x will decrease again. So we'll have k times k minus 1, x to now the k minus 2, because we took 1 away again when we took the derivative. You can see if I apply L'Hopital's rule enough times, eventually, since I'm subtracting 1 from the exponent each time, eventually this exponent will be less than 0, in which case we're at this case, and the limit will be 0. So if you have any power of x, e to the x is going to outgrow that. So you sometimes say exponential growth always outstrips polynomial growth in the end.